Hey guys, we left off with the exponential distribution and discovered that it was forgetful, and that in fact the exponential distribution was a generalization associated with a Poisson distribution where you expect only one thing to happen, such as death, a lifetime. Now, what we're going to begin with now is we're going to begin with the Poisson process. And with that Poisson process, we're going to include a rate, mu equals lambda, how frequently something is occurring. And what we'd like to do is we'd like to define W to be the waiting time until we just don't want the first occurrence because that's the exponential. So let's do the 5th, the 9th, the 10th. Now, because we're working in the continuous world, we often use W for a continuous function. We switch it to X, but W tells us that it's somehow a waiting time and continuous. But the other thing here is that I'm waiting for the nth occurrence. I'd like to put n in here, but traditionally we put in alpha. So we're waiting for the alphth occurrence. And clearly when alpha equals 1, we want this thing to be the exponential distribution. Now, when we derive distributions from properties, we frequently derive the cumulative one because that just is adding something up. But if we can do that sum, then we take the derivative to get the answer. So let's try to get the cumulative distribution of W, where we have little w greater than or equal to W. And this will be the probability that W is less than or equal to this little w, the cumulative up to that point, which is the complement of 1 minus the probability that W will be greater than W in a Poisson distribution. Now, here's the secret to developing this. If we have a waiting for the alphth occurrence, then the probability that W is greater than W can be stated in the following way. That this is the probability that fewer than alpha occurrences have happened in the time interval 0 to little w, because you had to wait longer than w for the occurrence to happen. Well, this is a fixed number of Poisson things happening in a fixed period of time. We can write down a formula for that. Now, in order to write down the formula for that, we've got first have to realize that the question is now being asked on an interval from 0 to w, where lambda originally was a rate in a unit time. So we have to make the lambda associated with the problem at hand, since now the unit of time happening in w, we have a new rate which is lambda w. So we have a Poisson distribution for our problem, and we want less than alpha occurrences. So 1 minus was in the problem, so we want the possibility from k equals 0, no occurrences, all the way up to alpha minus 1 occurrences of the Poisson distribution with its new lambda. So that's lambda to the w to the k, e to the minus lambda w, its new rate, over k factorial. So this is our f of w. Now, that looks kind of grungy and it doesn't look really nice, but I'm going to do a slight amount of calculation here. First, I'm not going to calculate that sum. I might try it and discover it's nasty. Instead, I'm going to immediately take the derivative, because that will give us our distribution for waiting for the alphth occurrence in a Poisson distribution. Now the derivative of 1 is 0, so it's just a question of calculating all of these derivatives. Well, If you write out the terms, you discover that you get lambda e to the minus lambda w minus, and factor out e to the minus lambda w here, and what's left is a sum of lambda w to the k minus 1 lambda over k factorial minus lambda w to the k lambda over k factorial. That's just writing out those terms and taking the derivatives. But how many things are left in the sum? So how many things are in this sum? Well, this was the derivative of the 0 term, so this is from k equals 1 to alpha minus 1. Now, A, I wrote terribly discussing here. B, that the values and equations look terrible, but let me just write them out carefully here. We have this f of w now, which is lambda e to the minus lambda w minus e to the minus lambda w. And we have that summation taking place from k equals 1 to alpha minus 1. Well, I'm just going to write out those terms. So the first term is simply lambda. If I put in k equals 1, that's 0. I got 1 in the bottom. And so we get the very first term of just a lambda. And now I put in the next term, and the next term, and the next term, and we discover it telescopes. Now this doesn't happen very much, but these all cancel to 0. And then the last term that will survive is when we put in alpha minus 1, we're going to get lambda times lambda to the w, alpha minus 1 over alpha minus 1 factorial. So even though that expression looked heinous, when we actually just took the time to write it out, the trick was the k over the k factorial caused it to reduce, and one of the terms turned out to be one larger than the other term with a change of minus sign. So now we have our f of w, which is lambda e to the minus lambda w minus e to the minus lambda w times lambda minus lambda w to the alpha minus 1 factorial. Again, if you just keep writing things out, nice things happen, and we get e to the minus lambda w times lambda w to alpha minus 1 over alpha minus 1 factorial. Well, that doesn't look grossly bad. Looks pretty good, actually. It's a slightly complicated expression, but we have an alpha minus 1 in there, factorial. Something's happened to alpha minus 1 times, and apparently the last alpha time came in as a multiplication at the end. So it appears that we have a distribution. Now, the distribution has a name. It's called the gamma distribution, and I'll point that out now. I'll return to that. Gamma is a special function. If you guys remember n factorial, 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, and 3 factorial is 6. Looks something like this. What would be kind of neat is if we could somehow create a smooth function connecting them. What's really odd is because of that 0 factorial, that smooth function has kind of a strange look, and I'm not sure what to do over here. I mean, kind of strange, but if we wanted to hook up the n factorial function to somehow a gamma of x that matches this, it's kind of a simple question. Was this definition of 0 factorial a reasonable thing to do previously? Didn't we just do 0 factorial so that we're able to simplify an expression that usually contains a 0 factorial in it? And it's nice that it's 1. Was that really necessary? It looks like a complexity. Well, what we're going to do is we're going to define an integral that turns out that when you do integration by parts makes things very nice. So I'm going to define, first off, gamma of t, to define an integral from 0 to infinity of y to the t minus 1 e to the minus y dt. And in order to make this work well, we're going to have t positive, and that's just a subtle point at the moment. So we're working on this region in some sense. Now, the next thing, however, is this integral is perfectly set up to do integrations by parts. If we let u equal y to the t minus 1, dv equal e to the minus y dt. Sorry, dy. I apologize. T is the parameter that comes out. Du is t minus 1, y to the t minus 2, dy, and v is minus e to the minus y. So this integral is uv, which is y to the t minus 1 e to the minus y, evaluated from 0 to infinity, minus the integral of v du. Well, the v's got a minus, so we'll make it a plus, and this will be the integral of t minus 1 y to the t minus 2 e to the minus y dy from 0 to infinity. Well, first off, this evaluation at 0 is 0, and at infinity is 0, so it's gone. This function is just t minus 1 times now the same integral before, except t minus 1 replaced with t minus 2. So that's gamma of t minus 1. So this integral has a very interesting property. It has the property that gamma of t is t minus 1, gamma of t minus 1. Now, that means that gamma of t minus 1 is equal to t minus 2, gamma of t minus 2, which we can plug in there and says that gamma of t is equal to t minus 1, t minus 2, gamma of t minus 2. So if I keep going this all the way down and we assume t is an integer, a natural number, why it looks like gamma of n is n minus 1 factorial. So this gamma function has a very sweet and nicely defined values. Now, the surprising thing is that it's a continuous function. It has values for any t greater than 0, which means we basically have defined something like minus 1 factorial, 1/2 factorial, pi factorial. We've got these strange values. It mimics our gamma function, and it mimics our gamma function in such a way that it actually goes through 0, 1. So this gamma function that we have created is mimicking our factorial function, and it does meet it here. And so does it go up? Does it go down? What does it do? Well, before we do much more investigation with that, let's go back to what we said was called our gamma distribution, our PDF. It had an alpha minus 1 factorial. Well, that seems to say that that we can use that function to put it in here and rewrite this integral in the following way. Now, the one thing about this integral that produced it, it made use of a repetitive Poisson distribution, which then we used the complementary process to get it. Well, the repetitive Poisson distribution, we've often found out the rate that something happens isn't a good measure, especially when we looked at the exponential, we wanted to invert it. So we're going to do the same thing here. We are going to develop a new parameter. So if we have a Poisson rate, lambda, then theta equals 1 over lambda produce the exponential distribution of f of x equals, and then we had the 1 over theta, e to the minus x over theta. That seemed to be a more viable way to define our distribution. Well, using the same trick, now we use the x variable. Our gamma distribution, where we are waiting for the alpha occurrence, we're going to have a Poisson rate of lambda. We're going to define theta equals 1 over lambda, and we get then x to the alpha minus 1, e to the minus x over theta, and we get gamma of alpha, and we get a theta to the alpha, because that's what happened when we switched over to this new rate over a period of time. This is our gamma distribution. And it gains its name from our using our gamma in there. It is a weighting distribution in a Poisson process, and we're waiting for the alphth occurrence. Now, one would think if lambda was the rate at which something was happening, then we would know very well that if we're waiting for a specific period of time, that theta is how long we have to wait. It would be interesting then to see if we're waiting for 2, if our answer is 2 theta, if we're waiting to 3, if our answer is 3 theta, because it seems if our average is going to be theta, then the average for waiting for multiple of them should be alpha theta. Well, how are we going to do this? Well, the easiest way to do this for the gamma distribution is to derive m of t. M of t is our favorite definition, right? How are we going to work out m of t? Well, m of t is the expectation of e to the tx, right? And our distribution, f of x, is 1 over gamma alpha, theta to the alpha, x to the alpha minus 1, e to the minus x over theta. This looks all kind of gross. So we're going to do the integral from minus infinity to infinity of e to the tx 1 over gamma of alpha, theta to the alpha, all that's in the bottom, x to the alpha minus 1, e to the minus x over theta, dx. Ooh, that looks downright difficult. Or is it? Seems to me that this and this can be combined, and we'll get a very nice looking expression. And it also seems to me that this integral looks a lot like a shift of this integral, because only this is being involved in here. So if you believe that this integral, this infinity in f, is equal to 1, which we're going to claim, then it seems that through a simple change of variable, we're going to be able to do that. Well, guess what? Exercise 3.2-7. You guys get to do that one. Complete that integral. What wonderfully happens is the following. M of t is 1 minus theta of t to the alphth power. And this makes the derivatives and calculation for the average and standard deviation quite trivial. M prime of 0, which is mu, is alpha theta. Sigma squared is alpha theta squared. Things work out just wonderfully. And indeed, if we're waiting for the third occurrence of something at a specific rate over a period of time, then we just calculate how many we expect to have happen in one and multiply by what occurrence we need, the third, to get the answer. Well, I think we should do a problem then. So we're going to do an example right out of the book because this is kind of messy and it's nice to see it match up and anything missing in there work out. So we're going to have calls arriving at a switchboard. At a rate of, let's say, 20 per hour. Now we're going to assume that this is a Poisson process. Why? Only one call can come at any given time, that one person's call is independent of another person's call. Probability is basically a binomial over a small enough subdivision of time. All right, so we'll set lambda equal to 20 calls per hour. Now we're going to ask a question. What is the probability that the second call arrives after the first 5 minutes? Now, before we proceed, it's pretty clear we're waiting for something because the question says, what's the probability that the second call, the waited for call, arrives after a continuous period of time, 5 minutes? And it seems like that 5 minutes could change. The probability the second call arrives after 7 minutes or 12 minutes. Now, the next thing to notice is that we have an hour up here and minutes down here. So what we're going to do is we're going to establish a Poisson process for the gamma function that uses the same unit of time. So we either have to convert to hours or we have to convert to minutes. So, since we're having 20 calls an hour, we divide that by 60 minutes, we set lambda equal to 1/3 calls per minute times 60 will be 20. So now we've established the same unit of time for the gamma distributions, period. Now if lambda is equal to 1/3, then theta equals 3. And once again, if you're getting 1/3 of a call per minute, it seems like that in 3 minutes you'll get your first call. So this is also understandable, that the expectation is it'd be about 3 minutes for your first call. So 5 minutes seems like a pretty good time for you, that you should get your second call, but to go beyond it, well, now that question is ready to be asked in the following way. Our random variable is the waiting time of at least 5 minutes, which will be the integral from 5 to infinity of our distribution dx, where our distribution now is the gamma distribution expressed in the units of this waiting time. Now, plugging that all in, this is the integral from 5 to infinity, and we've got our gamma value, so we've got gamma of 2, which is 1 factorial, that's a 1. The rate is produces theta equals 3, so we have a 3 squared in the bottom, which will be a 9. So we have x e to the minus x over 3 dx. And all of a sudden, this can be done by parts. So all I did is fill in theta, the period and time, and then reduce it to a problem that you know how to do. Now, when it's all done, this integral, when you do it by parts, you're going to get the evaluation of 8/3 e to the minus 5/3. Now, that doesn't have any special meaning to us yet in terms of probabilities. I don't know exponential values, especially negative ones. Turns out this is 0.504. So it looks like you got about a little bit more than a 50% chance that it's going to take more than 5 minutes for the second call to arrive. Seems to make good sense. The average is not exactly the 6 here. I mean, so 6 would be the expectation, and, well, we expect a probability greater than half, probably meet that. Now, since this is a fairly low value of alpha, this can be done in a different way. If you want the probability of that waiting time being greater than x, we know that that means it was the complement for less than x of that Poisson. So if we go back to the Poisson derivation, we could have done this calculation. And in this calculation, it's not that hard to plug in the x greater than 5, which was the question at hand. Our alpha was 2, so we want that only 0 or 1 things have happened before. So that's k equals 0 to 1. So this is 5/3 to the k, e to the minus 5/3 over k factorial. And this sum is only too long. We'll put in 0. Number to a 0 is 1. 0 factorial is 1. So we get e to the minus 5/3 plus, and now we put in 1. We get 5/3 e to the minus 5/3 over 1. And lo and behold, we get 8/3 e to the minus 5/3, because these two just add together. That's the exact value we did before. So these alpha distributions are literally repeated Poisson distributions, and you can calculate them in that fashion. Now, what do these gamma distributions, I called it alpha, what do these gamma distributions look like? Well, what happens is alpha grows, it spreads out the distribution. So with small values of alpha, they look like this, and it's very hard to get way out there because it's hard for something not to happen. But as something repeats, this thing is going to shift to the right because you have to wait longer for it to happen, so the average has got to be further out. And because there's repetitive things you're waiting for, there's going to be a bigger tail. So these things look like this. Common alpha equals 1, alpha equals 2, alpha equals 3. And so they look very much like a normal curve, and they have a habit of us spreading out to the right. Now, there's a very famous distribution. I'm going to leave you guys to read about this distribution. It just happens that it occurs so frequently that we give a name to it. Now, this very specific situation is when we set alpha equal to 1/2, lambda equal to 1/2, or theta equal to 2. Some very simple, nice value. And if we guarantee that the thing that we're waiting for is expressed as half of another number, which is weird, but we express alpha equal to r over 2. So if you're waiting for some occurrence, you can always solve for r here. With these two values, the gamma distribution becomes what we call the chi-squared distribution. It just allows us to specify things in a very specific manner. Now, if you think about it, this means that everything can be a chi-squared. And the reason for this is you just have to change your unit of time. Change your unit of time so theta equals 2. We had hours, lambda was equal to 20. When we changed to minutes, lambda was equal to 1/3. Therefore, theta was equal to 3. It's not hard to pick a unit of time so that this happens. And it's not hard to describe an r who divided by 2 is the theta that you're looking at. Hence, every single gamma distribution can be described as a chi-squared distribution. It's kind of like a unifying factor over all the gamma distributions. We refer to the R as the degrees of freedom, and we have tables of this to make things very nice to look up. We have not addressed or asked the following question. What are the characteristics of the chi-squared distribution? Since we have renamed everything, the best we can do is say that we have a repetitive Poisson distribution where a period of time has theta equal to 2. But what does this R mean, and why is it twice the size of what we're waiting for? That's going to be a harder one to explain. All right.